In the name of God, hello dear students, welcome back to Fairkhwa's website. I'm at your service, let's say as a physics teacher, to explain the physics curriculum. My name is Masood. Actually, I explained one section from chapter 1 for you. Right now, I'm gonna start the second section from the same chapter, chapter 1. And the title of this section is Tangential and Centripetal Acceleration. Right? I wrote a relationship. I divided the relationship between the tangential quantity and angular quantity into two, let's say, relationships. First of all, I want to, let's say, explain the first relationship between tangential speed versus angular speed. Tangential speed versus angular speed. Okay, actually, so far, we got information about angular speed, but till now, I don't know what the tangential speed is. Yeah, we have no idea about tangential speed. Even we have, let's say, we have no idea about the tangent itself. We don't know what tangent is. So this is a new expression for us, tangent. What's the tangent? Actually, tangent in mathematics refers to the straight line that touches the circumference of a circle at one and only one point, right? It's a straight line that touches the circumference, let's say, of a circle at only one point. This is called tangent, right? And tangential speed has to do with, let's say, with tangent. Tangent has to do with tangential and vice versa. So it talks about the direction, especially. If you say tangential speed means a speed that is, let's say, parallel to the tangent to the circle, right? Like this. So they are tangent to the circle. If I say tangential speed, it's a new, let's say, quantity for us, tangential speed. It means tangential speed actually is created along the tangent to the circle, like the line number 1, like line number 2, line number 3. This is called tangential speed in general, right? Let me explain the first, let me read the first definition of tangent to the circle. After that, I'll elaborate it for you. It says tangent to the circle. This is the definition of your textbook of tangent. It's the line that touches the circle at one and only one point. I told you, it's a line that touches the circumference of a circle at one and only one point. So right now, I'm gonna explain tangential speed for you. I don't know what tangential speed is. What's the tangential speed? It's this instantaneous. It's not average, instantaneous, right? Instantaneous means at each instance we have the value of the speed of the, for example, moving object along the circular track. Instantaneous linear speed, you see, I underlined linear speed for you. Underlined it for you, actually. It's instantaneous linear speed of an object directed along the what? Along the tangent to the object's circular track. So it's directed along the tangent to the circular track. Like this, like number 1, number 2, number 3. And I drew a, let's say, car for you. And we have a square, we have a, let's say, circular track. The car actually, I can say, moves around the, circular track, right? Whenever it, let's say, it moves around the circular track, actually, it gets tangential speed. It has a tangential speed, actually, toward the tangent to the circular track. Teacher, what happens to the tangential speed of the car when it reaches this point, for example, right? So it moves let's say, also to the tangent to the circular track. What happens to the car when it reaches this point, for example, this position, right? So the let's say in each position of the circular track, the direction of tangential speed as it clears it is from its name actually will be tangent to the circular track. This is called tangential speed. And tangential speed is a type of linear speed. It measures in meter per second. And we denote it as, let's say, Vt. You see, V sub t. V sub t. So we have a subscript of t under the V, and this is called tangential speed. Let me move to another, let's say, subject. And it's not another subject, actually. Let's say, I drew a, let's say, table for you. I separated tangential speed and angular speed. We want to compare tangential speed with angular speed. Actually, first of all, I want you to, let's say, take a look at the symbol itself. The symbol for tangential is, let's say, speed is Vt, but for angular speed, you know this information, omega, yeah? Omega for angular speed. All of the information within this part, actually, within the right side of the table, let's say it's background for us. But new information, let's say, is here. New information, let's say, we have new information about tangential speed in the in the left column of the table. Let me read the first one for you. I'm gonna read the first one. It says the first comparison is between the angular speed and tangential speed. This is our subject, actually. We concentrate on tangential speed especially more than angular speed because we knew information about it already, actually. We've got information about it in previous lectures. Tangential speed is instantaneous, you see, instantaneous linear speed. Actually, instantaneous means at any moment, at any instant of the circular track, actually, the object, let's say, has its own, let's say, has its own speed, right? So for a particular instance, there's a certain value of speed. There's a certain value of tangential speed. That's why we say instantaneous. It's not one number. Keep in mind that average, for example, average of everything is only one number, average. And it's not very accurate, actually. It doesn't describe the phenomenon, let's say, very accurately. But instantaneous is let's say, contains very accurate information because you concentrate on object at each, let's say, instant. At each instance, actually, at each moment, you concentrate and you study the motion of the object, and let's say at each moment. That's why it's a precise information, instantaneous linear speed of an object directly along the tangent to the object's circular path. This is the other definition, actually, for is it instantaneous linear speed. It's instantaneous, right? It's not average. And it's not angular speed, it's the linear speed. It belongs to linear quantities, actually. Instantaneous linear speed of an object moving around the circle and directed toward the tangent to the object's circular track. Like this one, for example, we have a particle here. This particle, let's say, moves like this. So the direction of the velocity along the circular track is directed toward the tangent to the circular track at each instant, right? The definition for angular speed is not new for us. Actually, I told you, the time rate of change of angular displacement, right? Omega. I wanted to focus on the left column of this table, actually. Number 2, found by Vt is equal to R omega. This is the rule for finding tangential velocity or tangential speed. Vt is equal to R omega. What do you say about the omega itself? You see, That's why I prepared the comparison, or I prepared the table for you, because omega has to do with Vt actually, and vice versa. I want you to rearrange the equation for omega. Here, omega becomes variable. Omega is equal to anything multiplied by variable, it goes down. So R goes down and Vt goes up. That's why omega is equal to Vt over R. This is the rule for finding angular speed. What do you say about the, let's say, unit of tangential speed? Because you say tangential speed belongs to linear quantities, that's why it's a linear velocity, but in a circular track. And it's measured in meter per second, but angular speed is measured in rad per second, as you know. Number 4, let's say, let me read number 4 for you. It says tangential speed Vt depends on the object's distance from the center of a circular path. What do we mean by, let's say, it depends on this distance from the center of the circular track? What does it mean? For example, we have a carousel. For example, we have a carousel. There's a horse here, right? There's horse A, and there's horse B. They are located at different, let's say, distances from the center of the circular track. What do I mean by from distance from the center of the circular track? Can I say, teacher, instead of distance from the center of circular track, can I say, let's say, axis of rotation? We can say this, right? So a tangential speed depends on the object's distance from axis of rotation. From the center means from the axis of rotation. So the longer the path is, the greater the tangential velocity is, right? The greater the, let's say, distance is from the axis of rotation, the greater the tangential speed is, and vice versa. I can say the smaller the distance is from the axis of rotation, the less the tangential speed is. So based on this information, I can say Vt of A actually is less than Vt of B. Why? Because let's say B is farther than A, let's say, compared to the center of the circular track, or compared to the axis of rotation. So the farther the object is from the axis of rotation, the greater the tangential speed is. Mathematically, I can say R is directly proportional to Vt. The greater, look here. Let me draw a circle for you. For each, let's say, horse, let's say there's its own circular track like this. So this is circular track for A. This is circular path for B. So I want you to compare, right? Compare the radius of each track. This radius of A, R of A, it's, let's say, small. It's very small. What do you say about the R of B? Actually, it's larger or longer than the R of B. So R of B is larger than R of A. Means radius determines the tangential speed. Radius actually has to do with tangential speed. If you say, for example, the farther the object is from the axis of rotation, what do you mean by this? Means the greater the, let's say, the radius is. The farther the object is, the greater the radius. In other words, simply speaking, I can say the farther objects from this axis of rotation have greater tangential velocity, have greater tangential speed, right? About the information within the angular speed, and I'm sure you know this information because it's not new for us. Angular speed, or omega, angular speed, is independent of the object's distance from the center. Let's say note. It says omega is independent of object's distance from the axis of rotation. What does it mean? Whether the object is far from this axis of rotation or near to the axis of rotation, it doesn't matter. All of the objects, let's say, have the same angular speed. And I told you in previous lectures, in previous lessons, actually, I mentioned this one. When you hear the word angular, actually, angular information of all points, let's say, are the same. So all of the points, let's say, on a for example, carousel, on a merry-go-round, all of the points on a merry-go-round or carousel or any rotating object have the same what? Have the same angular quantities. What does it mean? Delta theta for all of them is the same. Delta theta is the same. Omega is the same, right? Alpha is the same. So angular quantity in general does not change whether the point, let's say, lies, let's say, near to the axis of rotation or far from the axis of rotation. It doesn't matter. So angular quantities, let's say, are the same, right? But actually, tangential velocity or tangential speed is not the same because tangential speed depends on radius. But omega does not depend on radius at all, right? Let's move on to another. Let's say I wrote some hint and note for you. The first one, I'm gonna read the first, let's say, hint for you. It says linear motion in a circular track is called tangential motion. So someone, for example, someone asks you, and maybe this person is not in grade 12, maybe there's a student, your sister, your brother, your friend asks you, I don't know what the tangential speed is. I don't know what the tangential motion is. So tangential motion is the motion, let's say, is a linear motion, actually. Tangential motion, linear motion in what? Linear motion on a straight line? No. Linear motion on a curved line. Linear motion, let's say, above a circular track. This is called tangential motion, right? Tangential motion. I have a question for you. Does moon have any tangential motion when it, let's say, circles the sun or when it circles the earth or not? Think about it, right? So a linear motion in a circular track is called tangential motion. When R, another hint or note actually, when R is required in a question, for example, R is required, R is unknown. How do you find it? Actually, when you memorize the, let's say, the main rule, Vt is equal to R omega, you can rearrange it for R, you can rearrange it for omega. This is the main rule, Vt is equal to R omega. So I want you to rearrange it for R. R is equal to, R becomes variable here. R becomes unknown. Anything that multiplies by variable, it goes to the denominator. That's why omega goes down and Vt goes up. R is equal to Vt over omega. Let's say it's used for which purpose? For finding radius of a circular track. So about my question, did you, let's say, find the answer of my question? I said, does moon, for example, this is moon, right? This moon. And we have, by the way, this, let's draw another figure for you. We have Earth, an Earth, right? We have, this is Earth. This is our globe, right? And there's a moon. The moon circles the sun, circles the Earth. This is moon. It circles the Earth in an elliptic, in an ellipse, right? It's not in a circular, let's say, circular track. So the orbit of the moon about the Earth is not perfect circle. It's elliptical, right? It moves in an ellipse, actually. this is, let me write the name of the planet or the moon. So in this situation, does moon have any tangential speed or not? Of course, it has a tangential speed, let's say along the circular track. When it reaches here, for example, the tangential speed directed toward the tangent at each instant, right? You have to know this information. This is called VT for moon. And by the way, VT for moon is approximately 1 kilometer per second. Whenever you say one, the moon traverses 1 kilometer about the Earth. That's why VT for moon is, let's say, 1 kilometer per second. It's not per hour, per second. 1 kilometer per second. But VT for Earth is 30 kilometer per second. That's why, let's say, moon lags behind the Earth, and sometimes you see that the moon appears, let's say, in the sky during a day, not during a night, and moon displaces, let's say, each 50 minutes. Each 50 minutes, it let's say, it changes its position because it lags behind the Earth. Earth is faster than moon, and actually, Earth leads the moon, and moon lags behind the Earth. That's why I told you we can see the moon in different position of the sky. Even let's say during the day, we can see the moon. Let's say sometimes, right? So proof of the equation Vt is equal to R omega. Teacher, where does this equation come from? What's the origin of this rule? Vt is equal to R omega. Let me prove it for you, actually. Delta S is equal to, we start from here. Delta S is equal to R delta theta, right? R delta theta. This is the first rule of our textbook. Delta S is equal to R delta theta. Actually, any, let's say, change in arc length, any change in angle of rotation is taking place during a time interval. So you cannot neglect the time interval here. That's why divide both sides of the equation by time, because the changes in let's say arc length, and the changes in arc length and let's say angle of rotation, I told you, are taking place in a particular time interval. That's why divide both sides of the equation by delta t. So this one becomes what? Why does this fraction become actually Vt, right? Because we say if delta t is equal to, is very, let's say, close to zero. If delta t is very short, right? Delta t is very, very, very small. If delta t is very small, actually, if delta t is very small, circular track actually, and arc length does not remain as it is. Imagine you are in a car, actually. You are in a car, and the car rounds the circle in a very short time interval. And you are a passenger within the car. Maybe you don't, let's say, you don't, let's say, observe the, you cannot, let's say that the object moves around the circle. Maybe you realize that the object moves in a straight line. By the way, the object, let's say, circles the square. In this situation, because why do you feel this? You feel that the object, that the car moves in a straight line because the time interval is very short. So in the case of very short time interval, arc length delta S turns to what? Turns to delta X. So we deal with curved line in a, I'm talking about the short time interval. In a very short time interval, we deal with curved line as a straight line, as if we have a straight line, not curve. That's why delta S, you see, delta S turns to delta X, which is a linear displacement. So arc length is no longer arc length. Arc length turns to the linear displacement, delta x. And we have one more, let's say, one more note. If delta is very short, if time interval is very, let's say, short, delta t is very close to zero, omega represents instantaneous angular speed, not, let's say, average angular speed. It's easy, it's not very difficult. It takes actually 2 steps, but we have one condition. The condition, don't forget the condition. The condition is very important. In the case of very short time interval, if delta t approaches zero, delta s, arc length, turns to a straight line. Delta s is no longer arc length, it turns to the straight line. And omega represents instantaneous angular speed, not omega average. Thank you very much, guys, for watching this video, and bye-bye.